Alright, so let's talk about how intermolecular forces ultimately connect to the idea of physical properties. The idea to keep in mind is that the intermolecular forces of attraction are nothing more than Coulombic forces of attraction. And in order for you to undergo physical changes or to kind of explain why a substance is a solid or a liquid or a gas, ultimately what we're talking about is how much energy it takes to break apart these intermolecular forces of attraction. And the idea is that the greater your intermolecular force of attraction, the more energy you're going to need to break apart those interactions. So what you can see here is a list of molecules. And looking at the first one, we see that there is only carbon-carbon and carbon-hydrogen bonds. So we would regard a molecule as being nonpolar. And as such, we would say that it has London dispersion forces. Now, that being said, everything has London dispersion forces, but it is important to notice that for the first molecule, that will be the only force present. In the second molecule, we actually have a carbon-fluorine bond, and in the third one, we have a carbon-oxygen bond, which doesn't cancel out with anything else because there's no fluorine or oxygen bonds in the opposite direction. So this will render the molecule polar. And that means that the second molecule, the third molecule, and technically the fourth molecule, which also has that carbon-oxygen bond that doesn't cancel out, will have dipole-dipole forces. In addition, though, notice that we have a hydrogen bonded to an oxygen in the third molecule. That's also true in the fourth one, so hydrogen bonding is present in the last two. And lastly, the very last molecule has an ion present in combination with your polar molecule, so you have ion dipole forces. So what that basically means is that look at these molecules from left to right, the amount of intermolecular forces is increasing. And what that means is that it's going to get harder and harder to break apart the interactions going from left to right among these molecules. So one way to look at it is to see what the physical state of the molecule is at room temperature. And the molecule on the left is actually a gas because it has the weakest interactions among them all. The second one turns out to also be a gas at room temperature, but the boiling point of that molecule is higher than the first one, and that's a result of the fact that it has greater intermolecular forces. Now, by the time we get to the third one, where we have hydrogen bonding, that force is strong enough that the molecule is no longer a gas at room temperature, it's now a liquid. And for the one where we have an ion dissolved in it, not only is the molecule a liquid, but it has a higher boiling point than the first molecule. Now, I'm just saying higher because we're gonna get into the details of what these boiling points are, and to some degree how we can calculate them. But for now, we're gonna keep it general. Now, the other thing about intermolecular forces that is important to keep in mind is that they are additive. And because of that, when you're comparing them based on London dispersion forces, dipole-dipole forces, hydrogen bonding, or ion dipole, it's best to compare them so long as the molecular weights are similar to each other. And by that I mean, have a difference not greater than maybe 15 grams per mole, perhaps even 20. I might even go as far as saying 20 grams per mole might be semi-okay, but you're getting into murky territory at that point. All right, now case in point to show you how it's important to keep the molecular weights relatively similar to each other when comparing molecules. If you look at the three molecules right here, which I used in the previous example in a different lecture, the molecule on the left, the molecule in the middle, and the molecule on the right, they all have carbon-carbon bonds and carbon-hydrogen bonds as the only bonds present. So all of these molecules have London dispersion forces. That's all they have. But notice not only the formulas, but more importantly, the molecular weights. The molecular weights are vastly different. And even though all of them have London dispersion forces, pretty much what's happening is that the molecule here on the left, which has the lowest molecular weight, turns out to be a gas. The one that has intermediate molecular weight is a liquid at room temperature, and the one that has the greatest molecular weight turns out to be a solid. And the reason being is that the bigger the molecule gets, the greater number of London dispersion forces that it can have. And since they're all additive, um, the more molecular weight your molecule has, the more forces it's going to obtain and have available. The other thing too that needs to be considered is the surface area of the molecule. It turns out that the more surface area a molecule has, and by this I mean the molecular surface area, the shape of the molecule, the more London dispersion forces it will have. So let me show you an example of this. We have once again hydrocarbon molecules, carbon-carbon, carbon-hydrogen bonds. Only London dispersion forces are present in these molecules. But notice the shapes. The shapes are pretty different. And the interesting thing about these two molecules is that they have exactly the same molecular formula, 18 carbons and 38 hydrogens, which means that the molecular weights are exactly the same, but their shapes are vastly different. And the idea right here is that these shape differences give you different types of intermolecular forces, or different amounts, rather. And at room temperature, the molecule on the left is a liquid, whereas the molecule on the right is actually a solid. All right, now, the reason why this is happening is because we have greater intermolecular forces when the molecule is more planar or flat, as we can see right here, as it extends into longer and longer surface. And the reason why is because London dispersion forces are simply stated, delta pluses and delta minuses that get developed in the molecule as a result of electron movement in the molecule. And what you can see here, I just drew 5 pairs altogether, but they're well separated in the linear, molecule, the one that has the greatest surface area. If we write the same 5 pairs of delta pluses and delta minuses, in the first molecule, we have a lot more congestion. And because the charges are so close to each other, the molecule becomes a lot more unstable. And so it does not want to have that many charges present in a tiny region of space. And what that ultimately means is that really, in reality, the smaller molecule will only have maybe two, maybe one pair present among its structure, whereas the linear one will have 5 or more. And as a result of that shape difference and the fact that the charges are better well separated in the linear structure, you have more intermolecular forces present. Granted, they're all London, but there's more of them. And so the linear molecule ends up with a greater intermolecular force overall, which makes it be a solid at room temperature as opposed to the liquid form of the first molecule. Alright, now with that being said, we will start talking about the boiling points, the surface tension, the viscosity, and the volatility of the molecules, but I'm going to save that for the next video. So see you then.